I believe we speak in English, right? I think so. Welcome to welcome to everybody. It's a pleasure to have Mattia Calzi of the University of Milano. We'll speak about holomorphic function spaces on Siegel domains. Please, Mattia.
The topic I would like to discuss today concerns some spaces of holomorphic functions on a class of complex domain, which is that of homogeneous Siegel domains. To begin with, I would like to discuss at length, in some sense, the most simple case, which is the case of one-dimensional domains. So I start with a brief description of the case of the unit disk, and then I will highlight main properties of some spaces on the upper plane. So we start with the unit disk, and there are some classical spaces that can be considered on this space. So we start with the Bergman spaces, which are the spaces of holomorphic functions, which are LP integrable with respect to a suitable measure. Here I took the bag measure, but other measures can be considered. Then we have the Dirichlet space, which is the space of holomorphic function, whose derivative is in L2. Then we have the Hardy spaces, which are the spaces of holomorphic functions, whose restrictions to the circles centered at the origin have a uniformly bounded LP norm. And finally, we have the Bloch space, which is similar in some sense to the Dirichlet space, but in this situation, we have an infinity norm with a weight. Nonetheless, I'm not that interested in the bounded domains as in their unbounded realization. And canonical choice, in some sense, is given by the upper plane and in more dimensions by Siegel domains. So in this situation, we deal with the upper plane, which is known to be biomorphic to the unit disk by means of several mappings. In this case, I chose the Kelly transform. And on this space, the Bergman spaces I want to consider are these ones. So in this situation, the measures are translation invariant, where the translations are real translations. And in addition to that, so they are the product of a measure on the horizontal lines and of a measure on the imaginary axis. And this latter measure is given by a power function. I would like to discuss a little bit the definition, because there are two possible interpretations of the weight. So the weight y to the power s can be considered as a multiplier of the functions, as done here, and but also as a multiplier of the measure. The difference is that instead of taking y to the power s, we should take y to the power sp. Now, if p is finite, there is no difference up to a reparametrization of the spaces. But if p is infinite, this definition, interpreted suitably, gives rise to more spaces. And so it is more interesting in some sense. These spaces have some mixed norm counterparts that appear to be worthwhile considering when dealing with proofs and statements concerning the pure norm Bergman spaces. And the reason is that when p is equal to 2, basically Fourier analysis comes into play to deal with the restriction of the given function to horizontal lines, and so better results can be proved for spaces of type A2Q, and then by interpolation in some way we get better results also for spaces of pure norm. Nonetheless, in this talk, I'm only considering pure norm spaces. So these spaces are complete metrizable topological vector spaces, are Banach spaces when p is greater than 1, and are reproducing kernel Hilbert spaces when p is equal to 2. And the reproducing kernel of AQS is given by this simple expression, which can be then used to define a corresponding integral operator. So this weighted Bergman projector, PS, is a projector, self-adjoint projector of L2S onto A2S, where L2S is has the same definition of AQS, with the only difference that we take measurable functions and not only holomorphic functions. It is an interesting question to ask whether the Bergman projector PS acts as a projector or as an identity operator on other LPS or A2S spaces. In this one-dimensional situation, this question can be answered, and it appears that if S and S prime satisfies some necessary and sufficient conditions, for every F in the space APS, the operator PS prime acts as the identity operator on such F. And if P is greater than 1, then under the same conditions, the weighted Bergman projector PS prime acts as a continuous linear projector on the space LPS with image APS. And the reason why we need to restrict to P greater than 1 is that when P is strictly smaller than 1, the spaces LPS contain functions which are not locally integrable, and so the projector cannot be defined on such functions. Nonetheless, there are some sampling results concerning these functions, which in some sense can be used to discretize the weighted Bergman projector. And so the discretized weighted Bergman projector can be used to define continuous operators even for smaller p's. In order to do that, though, we need a suitable metric on our domain, which is the Average plane. And it turns out that the Bergman metric is a good choice. Bergman metric is defined taking the unweighted Bergman kernel, which is K1 in this situation, and I call it unweighted because it is the reproducing kernel of the space of functions which are holomorphic and belong to L2 with respect to the Lebesgue measure. And so in this sense, it is unweighted. Then we take it on the diagonal, we take the logarithm, and we define a Keller metric on the upper of plane in this way. Then we define the corresponding distance, which in this situation can be explicitly described. And we define lattices as, roughly speaking, maximal equally separated families of points. Then, if we take a sufficiently fine lattice, we can characterize the holomorphic functions f, which belong to APS, as those holomorphic functions whose weighted samples on the points of the lattice belongs to little Lp, and not only we can characterize AP, but also its norm up to equivalence, because this mapping is an isomorphism onto its image. And then, because of these results, basically, we may consider the discretized weighted Bergman projector, which is this operator from little Lp into the space APS. And under the same conditions under which the weighted Bergman projector acts as the identity operator on the space APS, for any lattice, we find that this discretized weighted Bergman projector is a continuous linear mapping. And if the lattice is sufficiently fine, this mapping is also onto and as a continuous linear section. Using this, the preceding result, which is also known as the atomic decomposition, because here it can be considered as the atomic decomposition where the atoms are the samples of the weighted Bergman kernel, we can prove that the first derivative, and so the other ones, are isomorphisms of APS onto APS plus 1, provided that, that S is strictly positive. So we can extend this scale of spaces APS to negative s in the most reasonable way using derivatives. Of course, we do not longer get spaces of holomorphic functions in general, but rather quotients modulo polynomials. And some interesting spaces arise in this extended scale of spaces. For instance, the space A hat to 0 is canonically isomorphic to the Hardy space, and actually it is the quotient of the Hardy spaces plus constant functions modulo constant functions. So it's basically the Hardy space. In the space when hat to minus 1/2 is canonically isomorphic to the Dirichlet space we saw on the unit disk, and the space A hat infinity 0 is canonically isomorphic to the Bloch space we saw again on the unit disk. And this, by the way, shows that the preceding result does not hold for s equal to 0 and p is equal to infinity, because otherwise the Bloch space would reduce to constant functions, which is, bounded functions, which is not the case. Again, using the atomic decomposition results, it can be proved that the canonical sesquilinear mapping between APS and AP prime S prime, where P is finite and P prime is defined as the conjugate exponent of P if P is greater than 1, and as plus infinity if P is smaller than 1. Then this canonical sesquilinear form induces an anti-isomorphism of AP prime S prime onto the dual of APS. And of course, if we add suitable derivatives to the functions f and g on the integral, we may extend these results to the spaces A hat PS. In particular, the Bloch space identifies with the dual of the weighted Bergman spaces of type L1, and the duality formula is this one. And finally, it is possible to find the exact boundary values of the spaces APS when S is strictly positive. In some sense, extending the results which are known for the Hardy spaces. So if we take a function in the Hardy spaces HP, it is known that these functions have non-tangential limits almost everywhere on the boundary, which is the real axis, and that these limits belong to a suitable LP space and characterize the function in the sense that if the limit is 0, then the function is 0. In this situation, the boundary values belong to suitable subspaces of the homogeneous basis space B minus SPP, and precisely to the space of distributions or quotients of distributions whose Fourier transform is supported on the positive half line. So we start with a distribution T, which belongs to this subspace of the homogeneous basis space B minus SPP, and we define a function on the upper plane by considering basically the integral in some sense of T against the Cauchy kernel, where the Cauchy kernel is the reproducing kernel of the Hardy space, and since the Hardy space is in some sense a singular value of the Bergman spaces A to S, it happens that its reproducing kernel is in some sense a sort of residue of the weighted Bergman kernels for the space for the weighted Bergman spaces A to S. And the reason why this should work is that if we take T, or rather if we start with a function in APS which belongs also to the Hardy space stage 2, and we define T to be the non-tangential limits of almost everywhere, then T belongs to L2, and this formula defines the original function f, because K0 is the reproducing kernel of the Hardy space. And since the Hardy space is dense in APS if P is finite, or at least weakly dense in APS, once one proves continuity of this mapping, this becomes an isomorphism. And in addition, the distribution T, from which we start, can be retrieved as the boundary values of the extension of T as a holomorphic function, in the sense that the restrictions of this extension to the horizontal lines converge weakly in the Biezos space as these lines approach the real axis. And the convergence is in the strong topology if P is finite. Now, since I want to consider function spaces on domains on several variables, now I need to introduce these kinds of domain. And to do that, I start with the definitions of homogeneous and symmetric cones. So we start with the finite dimensional real space Rm and an open convex cone, of course non-empty, omega in this space. Such a cone is said to be homogeneous if it does not contain any affine line and if the group G omega of linear automorphisms of the cone acts transitively on omega. And if in addition the cone is self-dual with respect to a suitable scalar product on Rm, then the cone is said to be symmetric. And in general, I define the dual cone omega prime of omega as the interior of the polar of omega. So omega prime is a subset of the dual of Rm, and the dual cone of omega prime is the cone omega itself under the identification of the bidual space of Rm with Rm. And this is a consequence of the fact that omega does not contain any affine line. And of course, if omega is a homogeneous cone, then omega prime is itself a homogeneous cone. And I need another definition. The cone omega is said to be reducible if it is not the product of two non-trivial homogeneous cones. The theory of homogeneous cones has been developed in the second half of the 20th century, and I need to recall some basic facts about such cones. And so, if we take a homogeneous cone, then we may find a triangular solvable group T, which acts linearly and simply transitively on the cone omega, and by transposition acts simply transitively on the dual cone omega prime of omega. And even though this group is clearly not unique in general, it is unique up to conjugations, and so it still is sufficient to define several important objects on the cone which are intrinsic. The first parameter is the rank of the cone, which can be equivalently defined as the dimension of the abelianization of T. And since T is a triangular group, its abelianization is canonically isomorphic to a product of R copies of the positive line, and so its characters, so its multiplicative function as values in the non-zero complex numbers can be expressed as power functions. And so the corresponding characters of T are called generalized power functions, and I will denote them by delta S. And since omega and omega prime can be identified with T once base points are chosen, the functions delta S can be transferred to omega and omega prime, and I would call them generalized power functions as well. Then it is possible to prove that the cones omega and omega prime have not only T invariant measures, but actually G omega invariant measures. So they're measures which are invariant under all linear automorphisms of the cone. And these invariant measures can be characterized as those measures which have density delta D with respect to the back measures on omega and omega prime for a suitable vector D with negative components in R to the power R. In addition, there are two more parameters which I need. which are these vectors with positive components m and n prime, which can be characterized by this property. So we start with the last line. So we take the measure on omega or omega prime, which has density delta s with respect to the invariant measure on the chosen cone, and we require this measure to have a Laplace transform defined somewhere. And this happens if and only if the real part of the components of S are strictly larger than the corresponding components of m and n prime respectively. And in this situation, the Laplace transform is defined at least on the dual cone and is equal to a suitable generalized gamma function times the generalized power function delta minus s on the dual cone. So on omega prime if we're starting with omega, and on omega if we're starting with omega prime. In addition, the generalized gamma functions have simple expressions in terms of the usual gamma functions applied to the components of S. In addition, D can be expressed as the vector -1, -1, -1, -1, -1, minus n minus n prime. Here are some examples. So the examples I will present are up to an isomorphism, all irreducible symmetric cones. So the first example is given by the case of rank 1, and it is the positive outline. In this case, all the objects are the usual ones, and there is nothing special about this cone. Then we have the case of rank 2, and we have here the Lorentz cones. In this case, there are at least two canonical ways to describe these cones. Here I chose this one because it is formally similar to the cones that will appear next. And so in this way, the cone appears as the cone of positive definite matrices, at least formally, because B is can be a scalar, but is usually a vector. In this situation, M and prime and D can be explicitly described. T is can be chosen to be the group of upper triangular matrices with strictly positive diagonal entries, at least formally, and the action is given by the product, some sort of conjugation of the given positive definite matrix with respect to this upper triangular matrix and its transpose, formal transpose. And finally, the generalized power functions can be described as products of powers of the determinant, at least formally, and the last entry. Of course, different choices of T give rise to different definitions of the generalized power functions. And finally, we have the case of rank 3 or higher. In this situation, omega can be described as a cone of positive definite matrices R by R over either the R field or the complex field, the real field of the complex field, or the division ring of the quaternions, or the algebra of octonions, but only if the rank is 3. In this situation, again, M prime and D can be explicitly described. T is again can be again chosen as the group of upper triangular matrices with non-zero positive diagonal entry, and the action is at least formally the same as for the Lorentz cones, as are the generalized power function, because they can be described as powers, products of powers of the principal minors given by the last rows and columns. Then, now that I introduced the cones, I need to introduce the Siegel domains over the cones. So we start with an open convex cone which does not contain any straight line and is not empty. For the time being, I do not require it to be homogeneous. Then I chose a Hermitian mapping phi from Cn times Cn into Cn, which is positive in the sense that phi of zeta, which is phi of zeta zeta, it belongs to the closure of the cone and is non-degenerate in the sense that phi of zeta is not 0 unless zeta is 0. And then and the Siegel domain associated with the cone omega and the Hermitian mapping phi is the open convex set of zeta z in Cn times Cn, such that rho of zeta z, which is the imaginary part of z minus phi of zeta, belongs to the cone omega. This is what is called Siegel domain of type 2. And if n is 0, so that the mapping phi is trivial, and the domain is simply the space of z in Cn, whose imaginary part is the cone omega, is called a 2 domain or a Siegel domain of type 1. Now, it is possible to prove that such a domain, D, is a homogeneous domain, which means that the group of biholomorphisms of D acts transitively on D, if and only if it is affinely homogeneous, which means that the group of affine automorphisms of D acts transitively on D. And this, in turn, is equivalent to saying that the cone omega is homogeneous, and it is possible to find a group T with the properties seen before, such that for every T in T, there is a complex endomorphism of G of Cn, such that the action of T on phi is the composition of phi and G times G. So if this condition is satisfied, the domain is a homogeneous Siegel domain. Otherwise, it is not. Notice, though, that the mappings of the form G times T, with G and T as in this case, are affine automorphisms of the domain D, but do not act transitively, of course. In order to get transitivity, we should act the natural action of the Shield boundary of D. So I recall that the Shield boundary of D, or so say, for instance, of a bounded domain, is the smallest closed subset of the closure of D, such that for every continuous function on the closure of D, which is holomorphic on D, the supremum of and which is bounded, the supremum of this function on D is the same as on the Shield boundary. In general, the Shield boundary is contained in the boundary because of the maximum order principle, but it can be strictly smaller, and actually it is strictly smaller in this situation unless the rank is 1, and in which case it is the boundary. And this Shield boundary has a natural action on the domain D, and of course also on itself, so it inherits a two-step nilpotent Lie group structure, and for this reason it is useful to describe it in this way and to identify by means of a canonical action. So the domain D decomposes as the union of the orbits of the group N, which is identified with the Shield boundary, and these orbits, the action of N and the action of the preceding automorphisms of D is transitive globally. Then I need one last parameter, which is this vector B with the negative components, which somehow determines or describes how the measure on Cn is deformed by these mapping G's only in terms of T. So why it is interesting to consider homogeneous Siegel domains? The first reason is that the upper half plane, which we considered before, is an example of a homogeneous tube domain, and actually of an irreducible symmetric tube domain. In addition, as I said before, Siegel domains have a nice foliation given by the orbits of the Shield boundary, which is analogous to the foliation of the upper half plane given by the horizontal lines. And in addition, since the Shield boundary has a natural two-step nilpotent Lie group structure, Fourier analysis comes into play and can be very useful to describe the various spaces of holomorphic functions on D. In addition, the family of homogeneous Siegel domains enjoys some universal properties in some sense, and precisely it is proved that every homogeneous bounded domain is biholomorphic to a homogeneous Siegel domain, and conversely, every homogeneous Siegel domain is biholomorphic to a homogeneous bounded domains. And so, in some sense, homogeneous Siegel domains can be considered as canonical unbounded representative of the class of homogeneous bounded domains. And finally, to distinguish between Siegel domain and homogeneous Siegel domains, besides the preceding property, homogeneity is quite useful. So we now deal with the generalization and extension of the preceding results to this more general situation. And well, the definition of the weighted Bergman spaces is pretty much the same with the suitable modifications. So instead of considering the positive line, its invariant measure, and the power functions on the positive line, we take a general homogeneous cone, its invariant measure, and its generalized power functions. So basically, this is formally the same. Again, these spaces are complete metrizable topological vector spaces, are Banach spaces if P is greater than 1, and are reproducing kernel Hilbert spaces if P is equal to Q. And the reproducing kernel can be described explicitly, well, up to describing the generalized power functions. And so we may consider the corresponding integral operator, which is the weighted Bergman projector. And again, it can be described where, under which conditions on S and S prime, vectors in this case, these operators, PS prime, acts as the identity operator on the space APS. Again, we may define the Bergman metric using, again, the unweighted Bergman kernel, computed at the diagonal, its logarithm, and then define a Keller matrix. And then we consider the associated distance and the associated notion of a lattice. And so we may define, define a weighted sampling operator, which again characterizes the holomorphic functions which belong to APS as those functions for which its weighted samples belong to literal P. With equivalent norms, again, if the lattice is sufficiently fine. This is the first result, which is not optimal, or well, in general, it is not known to be optimal. It is the optimal result is not known, and this result, as I state here, is not optimal. It's known to be not optimal. There are better sufficient conditions. Again, however, here I consider the discretized weighted Bergman projector, and as for the one-dimensional case, it is a continuous linear mapping from literal P into the space APS if the lattice is any, and if we take the lattice sufficiently defined, this mapping is also onto and has a continuous intersection. Here I would like to show some ideas behind the proof of this result, and I will be more sketchy and highlight only the main ideas, not the whole proof. So for the continuity part, this result, not the general one, of course, can be proved using the discretized weighted Bergman projector with positive kernel. And so we prove the continuity from literal P into LPS. Of course, we cannot go into APS because these functions are no longer holomorphic. And if P is greater than 1, proving then this discretized operator is continuous is equivalent to proving that the weighted Bergman projector with positive kernel is continuous on LPS. And this is related to the fact that there is some sort of quasi-constancy of the weighted Bergman projector, or rather of its moduli, and is known as Coryn's lemma. Then, using the invariant properties of KS of the weighted Bergman kernel, this object can be described as a convolution of F with this kernel, but only in the variables related to the group N, and then there is an integration on omega. So we use Young's inequality for the convolution, and then for the corresponding inequality between the functions on omega, we use Schur lemma, because we deal with operator with positive kernels. Concerning the continuous intersection, we deal with Riemannian sums, and precisely we start with the function in APS, so a morphic function. We take its weighted samples, and then we apply the discretized weighted Bergman projector, so we get this object. The only difference is that there are these constants Cj, which basically arise to make sure that this is a Riemannian sum approximation of the weighted Bergman projector. In some, of course, applied to F and not to any function. And it can be proved that this operator, which is obviously bounded, has an inverse because of the fact that the operator is the identity minus this operator to the power j, summed over j in the natural numbers, converge to a suitable operator. And then applying the sampling operator, or modified by means of this constant Cj, we find an inverse, well, at least a section of the discretized weighted Bergman projector. And this is basically the proof of the result. And for what concerns the continuity of the weighted Bergman projector itself, it is possible to prove results of this kind. So if S is sufficiently larger and S minus 2S prime is sufficiently small, then the weighted Bergman projector PS prime induces a continuous linear projector of LPS onto APS. Again, this result is not known to be optimal. There are optimal results in some cases for tube domains of the Lorentz cones, but in general the situation is unclear. And there are also some duality formulas. So we start with the assumption that either the discretized weighted Bergman projector or the weighted Bergman projector are continuous. And then we consider the corresponding canonical sesquilinear mapping between APS and AP prime S double prime, where S double prime is defined this way. And then we infer that if P is finite, and P prime is defined as before, this sesquilinear form induces an anti-isomorphism of AP prime S double prime onto the dual of APS. Now, concerning the role of the derivative, which we saw before, induces an isomorphism of between various weighted Bergman spaces. In this situation, different Riemann-Liouville operators has to be used. So, in this situation, given a homogeneous cone, it is possible to prove that there is a unique holomorphic family, which is a group under convolution, of tempered distributions on Rm, which are characterized by the fact that if the real part of S is sufficiently large, then this can be described as the measures with density 1 over the generalized gamma function at S times the generalized power function delta S with respect to the invariant measure. And it is possible to prove that if there is a free submonoid of the vectors with negative integer components, such that for every element of n, the corresponding Riemann-Liouville potential I of S has support at the origin. So convolution with I of S defines a differential operator. So if S is sufficiently large, then convolution with such differential operators gives an isomorphism of APS onto APS minus S prime. As before, these results are not known to be optimal. And to conclude, I would like to say something on invariant spaces, where the invariance is with respect to suitable representation or almost representations of the group of holomorphic automorphisms of the domain D. So we start with the unweighted Bergman kernel, which is in this case is k minus d1 minus d half, and we take its powers. Then it is possible to prove that this object is a positive kernel, which means that it is the reproducing kernel of the Hilbertian space of holomorphic functions, if and only if lambda belongs to the so-called Wallach set. This set can be described and it is can be decomposed into two parts: a discrete part given by r values, lambda 1, lambda r, the first of which is 0, and a continuous part which is an open up line starting from a lambda r to plus infinity. For symmetric and irreducible cones, these values lambda j can be described in a simple way. They can be described also for general homogeneous cone, but in a less transparent way. Then we denote the corresponding Hilbertian spaces of holomorphic functions by a lambda. And we observe that when lambda belongs to the continuous portion of the Wallach set, it is possible to identify these spaces A lambda as spaces of the type A hat 2S lambda for suitable S lambda. Since the Riemann-Liouville operators define isomorphisms of A lambda onto the Bergman spaces A2S lambda minus S, whenever S lambda minus S defines a suitable weighted Bergman spaces, which is not trivial. Otherwise, if we consider A lambda in the discrete portion of the Wallach set, then the Riemann-Liouville operators act trivially. And in fact, these spaces A lambda are somewhat singular, since, for example, if lambda is equal to 0, which is lambda 1, then this space is simply the space of constant functions, because the 0 power of the kernel is the constant kernel. Now, I said that these are invariant spaces with respect to suitable representations. So we define these representations. We start with the identity component of the group of holomorphic automorphisms D, and they call it GD. And then we define this map U lambda, so that U lambda of phi for every phi in GD acts on holomorphic functions by precomposition with the inverse of phi and multiplication with the suitable power defined suitably, of course, of the complex Jacobian of the inverse of phi. Well, if lambda over G, where G is the genus of the domain, at least when the domain is symmetric and irreducible, then this object is defined in an ambiguous way, and it is in fact a representation, or a continuous representation at least, of GD in the space of holomorphic functions. If otherwise lambda over G is not an integer, then this object is ambiguously defined, but since it can be lifted in some sense to the universal covering group of GD, and it can be lifted to a continuous representation of such a group, then we may at least assume that these power functions have been defined in such a way that U lambda is at least strongly measurable. And this assumption is made mainly because I want to compute integrals. And then, as I mentioned before, U lambda induces a continuous unitary array representation of GD in A lambda for every lambda in the Wallach set. Here I say continuous in the sense of ray representations, which I recall are basic representations, but define only up to the multiplication by a constant factor of modulus 1. So continuity is in the sense of the quotient and does not imply continuity as a map. Now, for this last slide, I need to assume that domain is symmetric and irreducible. In this situation, it is possible to define other invariant spaces, but only for suitably chosen values of lambda. So if lambda is lambda r, which is the last value of the discrete part of the Wallach set, minus a positive integer, then it is possible to define a new lambda invariant complete pre-Bergman space, by which I mean basically a space endowed with a scalar product, which is not Hausdorff, but is complete, and a lambda prime in such a way that U lambda induces a continuous unitary ray representation of GD in the Hausdorff space associated with a lambda prime. And so if lambda r is a natural number, then a prime 0 is defined and can be considered as a generalized Dirichlet space because it enjoys the same invariance property. Notice that lambda r is always half an integer, but it can be half an integer. So zero need not a prime 0 need not be defined. And there is also a unique result saying that if we start with a complete Bergman space H lambda of holomorphic functions, which is lambda invariant with its seminorm, and if the seminorm of H lambda extended by plus infinity is lower semi-continuous for the topology of compact convergence, and if U lambda is strongly measurable as a map on a maximal compact subgroup of GD with values in the Hausdorff space associated with H lambda, then either lambda is in the Wallach set and H lambda is simply the space H lambda we saw before, or lambda is lambda r minus a positive integer and the Hausdorff spaces associated with the H lambda prime and H lambda are canonically isomorphic. Of course, we cannot claim these spaces to be equal because anything basically can be in the closure of 0, but up to factoring out the closure of 0, these spaces are canonically isomorphic. That's all, and here is the bibliography that I quoted and cited, and of course it is by no means complete and makes no claim to be complete, and thank you for your attention.
Okay. Speaker. And I'd like to ask if there are questions or comments. So, anyone? Okay. Then, well, we should thank the speaker again for the talk. Thank you.
I'm sorry.